Hello everyone and welcome to PC Retro Tech. Today is the second in our series on 16-bit DOS games, and we're going to be looking at Grand Prix Circuit from 1988. It's a racing car simulator, and I've got it running on my IBM PC 5150 that has an Intel 8088 CPU in it running at just 4.77 MHz. And obviously this is a 4-color CGA game. So I'm using an original IBM CGA adapter, and the problem with machines in this era is that the processors were really underpowered. The CPU didn't have enough computational power to do full screen animation because it just didn't have the oomph to do all the calculations for updating every pixel on the screen every frame. But when you look at this game, you'll see that it's actually quite detailed. The graphics are, first of all, really exquisite. If you look at the dashboard in the foreground and the mountains in the background, it's been drawn really well. But it's also animated and gives the appearance that almost everything is moving. You can see that the road markings in the center of the road are moving. There's a gear stick that pops up every now and again. As you go around the corners are colored. And obviously as you move along, there are signs on the side of the road, and the mountains and stadiums and the clouds in the background are moving back and forth as you're going around corners. Even the fields on the side of the road are animated, and other parts of the screen are animated too. So the tachometer is animated, the steering wheel moves as you go around the corner, there's 2 rear view mirrors, there's a map, there's a timer, so everything's moving. So it really does give the appearance that the CPU is actually updating everything every frame. But there's really a lot of tricks going on here which aren't completely obvious when you first see it. So I'm going to try and analyze that in today's video. One of the things that I find most impressive about this game is actually the road itself. So obviously as a road gets further away from you in the distance, it gets smaller due to perspective. And if you know anything about perspective, you know that things get proportionally smaller as they get further away. Now, of course, proportions require divisions, but there isn't any floating point hardware in the 8088 CPU, so it's not using floating point divisions, it's just using integer divisions. And the problem with that is that the integer division unit in these CPUs is really slow. And so they obviously have employed a lot of tricks to make that fast. But the most impressive part is not in the road itself, but in the main game here, that you also have cars on the road. And the reason these are impressive is because they're sprites. And these sprites don't have to be entirely on the screen. They can be half on the screen and half off the screen. So this is particularly impressive because if you think about how a machine like this would work, it doesn't have any sprite hardware in it. It must be drawing everything using the CPU direct to the screen buffer, but the screen buffer wraps around. And exactly the same thing happens with the road signs as well as they're going by. They can be half on the screen and half off the screen, and when that happens, you would expect them to wrap around. So if the sign or the car disappeared off the left, you'd expect it to reappear on the right. And that is not happening. Now you might think that's easy to solve. Well, I just look at each pixel and I figure out whether it should be on the screen or not. If it should be on the screen, I draw it, and if it shouldn't be on the screen, I don't draw it. That's easy, right? But you have to remember that in order to make decisions like that on a per pixel basis, you have to do a jump that is conditional in your code. So you would jump to one subroutine if the pixel was on the screen, and you jump to another subroutine if the pixel wasn't on the screen. Now that conditional jump was very, very slow in these processes, and so you couldn't afford to do very many of those. And sprites themselves are actually very complicated to draw. They're not like the background stuff, not even like the road or the mountains that are moving, but they are being layered over the top of the background. And in fact, if you look at these cars, you can actually see through their windshields through to the other side. So it's not just a big square box that's being drawn on the screen. You've actually got, an overlay or a transparent overlay that's being drawn on top of the graphics in the background. And so this requires a lot of computational power. Sprites are very computationally intensive to draw compared to other screen elements. And so obviously they've used a whole slew of tricks. And when we slow down the video in this game and take a closer look, we'll see what some of those tricks are and how they fool the eye and yet manage to give you the appearance of really smoothly moving sprites that can be half on the screen and half off the screen. So I was actually so impressed with this game, especially the road at first, that I decided to write my own version of this. Obviously not anywhere near as complicated because I'm not an entire team of programmers, but I decided to just emulate the dashboard, the road moving, and the mountains in the back moving. So I'll show you that a little bit later in the video, what I came up with. And of course that means I had to do all the perspective computation for the road. Now I'm not going to go into all the mathematics behind that, but I'll give you a little bit of a hint as to how it's done without using the integer division unit in the processor. And we'll take a look at some of the other elements in this game and how they're using tricks to fool the eye into believing that you're seeing 4 or 5 frames a second animated, when in fact the reality is they're really saving pixels absolutely everywhere and using a bunch of tricks to make you think that it's being updated 4 or 5 times a second when in fact it's not.
So the first thing I want to discuss is this car, which is appearing for the first time in this frame. And I think it would have been too obvious if it had been a big rectangle like this, but I think they're helped out by the fact that it's an L shape, and so there's not very much of the car showing. Now the other thing to notice is that this mirror is almost the same width as the car, and I think they've realized that they're going to have to cover up the bottom of the car because otherwise it would hang over the dashboard. And so because they're going to have to update this region all the time to cover up the cars, they thought, well, why not make some use of this? And that's when they had the idea to put a rear view mirror here, which is updated actually every frame. And it's kind of confirmed if you look over the right hand side, there's also a rear view mirror there, which serves exactly the same purpose for sprites on the right hand side of the screen. So if I advance to the next frame here, you actually get all the way to the bottom of the car. This line that runs under the exhaust is the exact bottom of the car, at least this portion of it. And I think that what they're doing is they're bringing the car on in blocks here. In fact, if I bring on the last frame here, you see that this left wheel here matches up exactly with the left-hand side of the screen. Now, it's not entirely clear exactly where the blocks are, but I suspect there's one for the right wheel, another one for this wheel, including probably the right-hand side of this fender, and I'll explain why in a moment. Then a block here, which is the one that we saw in the sort of L shape that we had on the first frame, then this block for the second frame, and then this final block here. Now the reason why I think the fenders are included is because when the car is on the left hand side of the screen here, you need to see the right hand 2 wheels of the car and the right hand side of this fender. When the car is on the right hand side of the screen, you need to see the left hand 2 wheels and the left hand side of this fender. So it makes sense that they have to break up into blocks roughly where these fenders are anyway. And so that's what I think they're doing. I think they're breaking this up into about 5 different sprites, maybe more. And this means that you don't ever have to have a sprite hanging over the edge of the screen. A sprite is either on the screen or it's not on the screen. So breaking larger sprites up into smaller sprites is one technique for getting smoother animation without having to write really complicated sprite routines. So here's another car appearing on a screen here, and you can see the right wheel just popping over the edge of the screen here. And then in the next frame the entire car is there, and of course the left hand side of that car is very suspiciously exactly up against the left-hand side of the screen. So I don't want you to think that this is all trivial. The cars are shown from a lot of different angles, and of course they have to get smaller as they go off into the distance. So there's a lot of different sprites that they have to draw here. And I'm sure that when the cars are very small and pop off the side of the screen, this can all happen in one go. It's only when they're very large and near the dash that you have to worry about bringing them on in blocks. Another trick that they use, which is really funny, is when the car comes up in the middle of the dash rather than in front of one of those rear view mirrors, you just crash into it, and that's the end of the game. So they never have to show half the car in the middle of the screen. So I'll say a few words about the scenery. I'm going to leave the mountains and roads for the next section when I'm actually talking about my own demo. But I'll talk about these fields here, and you can see that it looks like they're moving, but actually the red stuff in the fields is actually fixed. It's only the white bits that are being updated, and these are narrower, and so that means less updates when drawing the fields. So it's the same for everything really. In the map in the upper left corner, it's just some little white dots that are being updated. In the timer at the right, there's just some numbers being changed. And the steering wheel is not moving at all except for the middle portion. It's actually just that little red dot moving backwards and forwards. So all of the game is like this. They're using lots of tricks to give the illusion of a lot of movement, whereas actually there's very little of the screen is actually being updated between each frame.
So this is the little demo that I wrote, and you can see it's much simpler than Grand Prix Circuit. It just has a dashboard in the foreground, mountains in the background, and an animated road in between. And as you move the car left to right, the mountains and the road both move. You can also slow the car down, and you can even stop the car if you want, and you can speed it back up again. And believe it or not, those are the main elements that you need for a game like Grand Prix Circuit, other than, say, sprites. Now, I have coded up sprites elsewhere, but I'm not going to talk about those today. Instead, I just want to talk about how the animation works here. So in the upper left-hand corner, you'll see there's a little number, and that is used to compute the number of frames per second. And I get about 8 frames a second here, which is twice Grand Prix Circuit. But of course, I'm doing a little bit less work here, and so it sort of all averages out in the end. Now, the graphics themselves I didn't draw because I'm absolutely no good at pixel art. Instead, what I did is I took photographs of mountains and the inside of a car, and I converted them to a 4-color palette using a graphics program, and that gave me some PCX files, which is a graphics format from way back in the day. It is a compressed format. It uses run length encoding, but it's simple enough that I was able to write my own program for reading PCX graphics and displaying them on the screen. So that's actually done in assembly language, and it's really fast. Now, the mountains in the background are themselves animated, and you can see they move left and right. Of course, if you want to move 4 pixels to the left or 4 pixels to the right, that's easy because there are 4 pixels per byte in screen memory, so you're just moving bytes about. But if you want to shift by 1 pixel to the left or 1 pixel to the right at a time, that's much more complicated. Because you'd need to shift within the actual bytes, and this requires additional computation, which is really too expensive to be done here. So there's a couple of ways around it. You can just jump by 4 pixels at a time, and I think that's actually what I do here from memory in this particular version of my demo. The other way around it is to make 4 copies of the image in main memory and just copy from the correct one. So each one is shifted by 1 pixel from the next, and so you just choose the right image and do a really fast memory copy from screen memory, from main memory to screen memory. So that's basically all there is to the mountain. Although mountains are large and they look big on the screen, they're actually only 12 pixels high here. So it's a really small amount of screen real estate that's actually being updated, and it really doesn't take very much of the computation time. Unfortunately, the road is a different story altogether. That is very hard because you need to do a computation for each of the 36 lines, each of the horizontal lines that makes up the road. And you can see that there are 6 different values that you're going to need for each of those 36 lines, one for each of the left and right hand sides of each of the road elements. You've got a left hand road marker, a middle marker and a right marker. So all of those values could be stored in lookup tables, so you could do 6 times 36 for example, and that would avoid doing divisions. But this doesn't quite work, unfortunately. It's basically the right idea, but I'll show you what happens. If I go right over to the left here, the road is much narrower, so the width of the road and all of the road elements depends on where you are to the left or to the right. And I could go thousands of pixels over to the left and thousands of pixels over to the right, so I'd have to multiply 36 by 6 by thousands, and that's more memory than I have in this machine. So this is a 640 kilobyte machine, but this program will run just fine on a machine with a lot less memory. And in fact you want to use no more than about 64 kilobytes, because that's a segment in memory, and addressing anything more than that is more complicated and takes longer. So you really can't use lookup tables in the way that you might imagine. So there is a trick to making this work, and it basically boils down to this. If I am starting from about here, anywhere over to here, or let's say here, then there's maybe only 256 different positions of the road here. And so I can store the values directly in a lookup table for those. But if I go over, much further over to the left or the right, then I'm going to get values that are much bigger than 256. So I have to add some multiple of 256 to the number of shifts if I want to go much further to the left or the right. And the way I can do this is using a second lookup table, which is for multiples of 256. So I have one lookup table for numbers under 256 and one for multiples of 256, and I just add the values from the two lookup tables together. That's basically the only trick that's used here. Now I'm not going to go into all the details, it's a little bit more complicated than that, but I will mention that when you're doing the road itself, you don't really need a different value for each of the road elements. You only need a value for the width of the road, and you can draw all of the other things as a proportion of that width. So for example, the right hand road marker might be 10% of the width of the road, and so again you need some lookup tables to compute those values, but it's actually pretty straightforward to figure out how to do this. The main issue that you have with integer divisions is if you just do the naive thing and just use ordinary integer divisions, what happens is you are throwing away the remainder when you do an integer division. And the remainder is really important for doing rounding. So when you use floating point arithmetic and you do a division, you get a decimal point and you can round to the nearest value. But you can't do that with integer divisions. So the trick for getting around this is something called sub-pixel rendering. And the way this works is when you're doing your integer divisions, you just multiply both of the values you want to divide by, let's say 8, and you'll still get the same quotient because you multiply them both by 8, but you'll also get a small remainder, or at least you're able to extract a small remainder, and you can use that remainder for rounding. And this gives you much more precise values, and so everything looks a lot smoother when you use sub-pixel rendering. So I actually do that here. Even so, those middle road markers look a little bit jagged at times, and they don't look completely straight. And this is because the sub-pixel rendering is not perfect. And we noticed this in the Grand Prix Circuit game, and so I'm pretty sure that they're doing roughly the same thing that I'm doing. I don't know the exact algorithm they're using, but after a lot of experimentation and noticing that I get the same jaggies that they do, I'm pretty sure we must have ended up with pretty close to the same sort of algorithm. So that's basically all there is to it, and I'm not going to say much more about the program today. So thanks very much for watching, and if you enjoy this sort of content where I analyse CGA games, then don't forget to subscribe. Leave a like on the video because that really helps out a lot. And we'll see you in a later video. Thanks and bye.